Hello everyone. So today we're talking about the Markov chain Monte Carlo for Metropolis-Hasting-Sampler. And in part 3, we're taking a look at an alternative example. So the question is, how do we simulate samples from a stationary distribution, which will be the Cauchy distribution? Before we dive into this question, let's take a look at what really is a Cauchy distribution. According to Wikipedia, a Cauchy distribution is known as a symmetric continuous probability distribution with no expected value. The PDF of the distribution is shown as below, with x taking values from negative infinity to positive infinity. There are two major parameters controlling the behavior of the PDF. The first parameter is the location parameter, denoted as eta, and the second parameter is the shape parameter, denoted as theta. The graphs of different Cauchy distribution PDFs are shown on the right side of the screen. Notice that if we tweak the value of x0, the center of the PDF is going to have a disposition to the left from if we change it to -2. And by changing different values of the theta, which is the shape parameter, we can see that the flatness of the PDFs are going to change. And for the application part, a Cauchy distribution is widely used in quantum mechanics when scientists use to measure the energy distribution in an unstable state. And also in the study of robustness distribution of different matters, scientists use the Cauchy distribution to measure the randomness of a matter. And again, the logic of Metropolis-Hasting-Sampler is shown over here, but since it is demonstrated in part 2, I'm not going to go through every detail of it. So in this case, the little f is going to be the Cauchy distribution, which is the distribution we are generating. And for the proposal distribution, again, this time, we're using a normal distribution. So how do we program the algorithm in R? Well, according to the algorithm, from step 1, we select a proposal distribution denoted as G with conditional xt for the generation of the target distribution. The code is shown as on the right with our norm, since our norm denotes a normal distribution, and xt is the current state of the Markov chains. So before we move into the second step, we always have to check the supporting set of a proposal distribution must be equal to that of the target distribution. So by taking a close look at two sets of distributions, the normal distribution, which is the proposal distribution, have a supporting set from negative infinity to positive infinity for all x values. That matches the supporting set of the Cauchy distribution. So the condition is met. Let's continue to step 2. For step 2, we're going to generate x0, which is the initial state of the Markov chain from the proposal disposition. And notice that the code outputs a value that is -0.62. This is the value where the Markov chain starts from. And in step 3, we have 3 parts. The first part we're going to do is to store the current state of Markov chain xt, which is the current state, and generate y, which is a set of values that follows the distribution of the proposal set. The code is shown on the right. And for part B, we're generating a uniform distribution that has parameters 0 and 1. The code is shown on the right. And for part C, we're going to set xt plus 1 equals y, which is the next current state after the previous current state. And then we're going to set a accept and reject algorithm. If the uniform distribution satisfies the inequality denoted as below, then we're going to generate the value. Else, we're going to set the next state just equal to xt. And in step 4, we're incrementing t by setting a variable for t plus 1, and in part B, we're repeating the overall process of the algorithm from step 1 for 10,000 times. And this can be done if we store an n variable for 10,000, denoting the number of times repeating the process, and this process can be done with a for loop. So by an overview of the algorithm in R, notice that in step 2, we produced x0 as the initial state of the Markov chains, and in step 3, we produced xt as the current state of the Markov chains. And in part B, we produced U01 as the uniform distribution used for the accept and reject process. And in C, denoted as this part of the code, we are actually performing the accept and reject algorithm inside of the Markov chains of the Metropolis-Hasting-Sampler. So how do we determine whether the algorithm does its job? For the sampler performance evaluation section, we're tweaking the variance sigma with 10,000 repetitions for all proposal distributions, and the outcomes are shown below. So are the Markov chains stationary for all the 4 outcomes? So if we take a look at the first one with sigma 0.05, we can see that all the values generated in the Markov chains from the proposal distribution remains unstationary, unfortunately, because all of the values are falling out of the range of the confidence interval. And if we take a look at the second Markov chains, we can see that the majority of the values lie within the confidence interval, which makes the proposal distribution with sigma 1 generating a stationary Markov chains. And the third one with proposal distribution with sigma equals to 5, we can see that the majority of the values lie within the confidence interval, so which makes the third outcome a stationary Markov chains. And the fourth one as well. Take a look at the first Markov chains. According to the law of large numbers, if we generate enough amount of the Markov chains in the output with more times of repetitions, the unstationary Markov chains can remain stationary in the future. So let's make this one stationary. So if we tweak the number of iterations n, the outcomes are shown below. Notice that the first outcome is just identical to the outcome of the Markov chains with sigma equals 0.05, and the rest of the 3 outcomes as well, but instead I just simply increased the number of repetitions. So the first one of the outcome is definitely not stationary because it's just the identical outcome, but if we increase the number of repetitions to 50,000, we can see that the numbers are attempting to get into the confidence interval, which makes this one getting stationary, and that is a good thing. And also for the third one, if we repeat it more and more, we can see that the pattern of the Markov chain gets more and more stationary, and if we complete doing it for a million times, it becomes completely stationary. So back to the slides, tweaking the variance with 10,000 repetitions, but this time we're checking whether the Markov chains are efficient enough or not. So by checking the efficiency, we decided to output the rejection rate of the Markov chains, and the rejection rates are calculated by the number of rejected cases rejected by the accept and reject algorithm inside of the Metropolis-Hastings order divided by the total cases. And we can see that the only one that is satisfying the rejection rate between the interval 15% and 50% is the outcome with sigma equal to 1, which means that the only proposal distribution we're using for the normal distribution in order to produce the Cauchy distribution has the sigma equal to 1. We have performed all the major steps of the sampler performance evaluation. Now let's take a look at, do we really get random numbers from the standard Cauchy distribution by using this Markov chain, or the algorithm did its right job to produce the right kind of the Markov chains in order to produce the standard Cauchy distribution. So the results are shown below. In the histogram, all the values are represented by the generated numbers from the algorithm, and the line represents the theoretical output of the standard Cauchy distribution. So the distribution of the histogram and the distribution of the line matches together, which states that the algorithm generated the correct sequence for the standard Cauchy distribution, since all the values in the histograms match the theoretical outcomes. And that's it. Thank you guys for listening.